Death Valley, California. It's the hottest place on Earth and one of its most extreme environments. But despite its outrageous heat and remote location, every year more than 1 million people travel to Death Valley to experience its stunning landscapes. How did these form? What happened here to create such a dazzling country? Join us as the geology students of Bryn College lead you on a tour of the geologic story of Death Valley. Almost 2 billion years of colliding plates, iconic fossils, water, ice, sand, and salt. Land doesn't just exist. It has to be built. The area that's now Death Valley began forming almost 2 billion years ago. Earth was different then. All life was single-celled and lived only in the oceans. The continents were lifeless rock and arranged very differently than they are now. Geologists can reconstruct where continents used to be using Earth's magnetic field. As lava cools, any iron minerals in it will point toward the North Pole. They remain frozen in that orientation, even as the continents move them around. Geophysicists, like Bryn faculty member Arlo Weil, can then measure the orientation of those iron grains and model where they must have formed, relative to Earth's magnetic north. Every so often in Earth history, the continents have all collided, forming giant supercontinents. About 2 billion years ago, all of Earth's continents collided to form a supercontinent called Columbia. It was in this collision that the first rocks of Death Valley formed.
It happened here when Antarctica collided with the west coast of North America. An arc of volcanoes similar to the Aleutian Islands got trapped in between the colliding continents. These volcanic rocks were buried down deep into the earth and got metamorphosed. Also from this collision, we had a huge mountain range that was created. This was the first rocks of Death Valley.
These mountains are not that range. The first mountain range eroded to nothing long ago. The only thing that was left was the core. That highly metamorphosed core became the basement rock on which all of Death Valley was built. Unfortunately, you can't see the oldest rocks in Death Valley. There's a few of them exposed in the Black Mountains, but for the most part, they underlie the entire valley. They're the basement rocks, which is what the entire valley is built on. So this is what the basement rocks of Death Valley probably look like. This rock here is called a gneiss. You can see that the minerals within the rock have been squished and banded. This probably formed during the continental collision that formed this rock. So this is really what the basement of the rock looks like, even though we can't see it.
Geologists can figure out when a rock formed using radiometric age dating. They take samples of the rock in the field, then bring them back to the lab, cut them, attach them to glass slides, polish them, and examine them under a special kind of microscope. There they can identify minerals that often include radioactive isotopes in their crystal structure, like zircons. Once they find key minerals, geologists use tools like electron microprobes to map the ages of the mineral and the rock. This is how we know that Death Valley's basement rocks formed 1.8 billion years ago during the assembly of the Columbia supercontinent. But supercontinents don't last long. They can't. They block heat from escaping Earth's interior. That heat builds up, and eventually it forces its way out, causing the continent to break apart. About 1.5 billion years ago, the Columbia supercontinent began to break apart in a process called rifting.
So we don't see a lot of evidence here of Columbia rifting apart, but there is evidence down below in these mountains behind me, which are the Panamint Mountains. So what happens in a rifting environment is that the continental crust is spread apart, and that allows mantle material to rise up and form igneous intrusions, which form granites. So if we were to be able to see down under here, we could probably see some granites. So the granites that formed at Death Valley formed during the Columbia rifting, and we can't see them because they're in the basement of this formation, but here we have a sample of granite. We have minerals that cooled really slowly to form these large pieces. In it we can see feldspars and quartz. And this is a good example of what we would be able to see if we could really see that, have access to that stuff in Death Valley.
The Columbia supercontinent did not rift all at once. Antarctica stayed connected to North America for hundreds of millions of years, and the area that is now Death Valley was right in the middle of the giant Antarctica North American continent. This was about 1.2 billion years ago, and the Death Valley region occupied a low-lying basin. But it wasn't the basin we currently see. The basin we see today formed very recently. This ancient basin was much wider, and when it filled with water, it would have looked more like a shallow inland sea. Rivers from the surrounding mountains brought sand and mud, and layers of sediment built up over time. For the sand and mud on the bottom, the weight of overlying sediment eventually compressed them into rocks, forming sandstones and mudstones. We see these rocks all over Death Valley today. Geologists call this stack of sedimentary rock the Pahrump Group, after nearby Pahrump, Nevada. It is in these billion-year-old rocks of the Pahrump Group where we see the first evidence of life at Death Valley, stromatolites.
So here we have some evidence of some stromatolites, which are some of the oldest evidence of life on Earth. And this is a Proterozoic dolomite, which is a carbonate rock. And the way that these stromatolites formed is that there were microbial mats on the seafloor, and these are microbes that photosynthesize. So when sediments were falling on top of them, or in this case carbonates were precipitating and falling on top of them, they had to move up to reach the sunlight again. So that's why we get these layers of these rounded sort of shapes.
For 600 million years, the Pahrump Group slowly grew. Stromatolites formed vast reefs across the shallow sea that covered Death Valley. And during that time, Earth was changing. Starting around 700 million years ago, Earth went through a catastrophic climate change. And for millions of years after, almost the entire Earth froze. Geologists call this period Snowball Earth. We're not entirely sure what caused this. Maybe Earth's continents were situated on the equator, absorbing less heat from the sun than open water would. Maybe algae began to pump more oxygen into the atmosphere, where it reacted with and neutralized methane, a famous greenhouse gas. Or maybe it's because the sun was 6% fainter back then. Regardless of the cause, as Earth cooled, a runaway cold cycle began. As temperatures dropped, more ice covered Earth's surface. This reflected more sunlight away from Earth, which caused temperatures to drop even further. Eventually, the whole Earth was covered in ice, even the equator, where Death Valley was located.
Death Valley is one of the best places on Earth to see evidence of Snowball Earth. Many of the rocks in the Pahrump Group show direct evidence of global glaciation.
Some of that direct evidence can be seen here, at Sperry Wash, just south of the national park. The rocks here are part of the Kingston Peak Formation, a stack of sedimentary rocks that likely formed during Snowball Earth. These are a special kind of sedimentary rock, called a diamictite. Diamictites usually form from glaciers. When debris falls onto a glacier, it rides along as the glacier moves. If the glacier ends at open water, any debris riding along with it will be dumped into that water. The result is a sedimentary rock that consists mostly of mud, mixed with clasts of other rocks in a wide range of sizes. Another line of evidence for Snowball Earth at Sperry Wash comes from the color of the rocks, a vibrant red caused by iron oxides. These kinds of iron-rich sedimentary rocks are rare in Earth history. To form, the ocean must accumulate dissolved iron. This is difficult because any water in contact with Earth's atmosphere will be rich in dissolved oxygen, which will react with the iron and cause it to rust out. During Snowball Earth, ice would have sealed the oceans, cutting off the ocean's supply of dissolved oxygen. Dissolved iron could have slowly built up in the oceans, and any later influx of oxygen would have suddenly oxidized the iron, which would precipitate out, forming these iron-rich layers. The diamictites and iron-rich layers both point to glaciers covering Death Valley about 700 million years ago. But we find the most dramatic evidence of glaciers further down the canyon.
This right here is a dropstone. We see a lot of these as evidence of Snowball Earth. A dropstone is basically a large boulder that has been transported by a glacier, rafted out inside of an iceberg, and then finally when that iceberg melts, the dropstone, the large boulder, drops into the sea. It lands in these fine layers of mud and deforms them. And so basically you wouldn't expect to see this in any other environment but that of a glacier.
A lot of the evidence for Snowball Earth isn't visible to the naked eye. A lot of it is geochemical. To uncover this kind of evidence, geologists take samples in the field and bring them back here to a lab like Pedro Marenco's geochemical facility at Bryn College. Here, Pedro and his students can measure the precise composition of rocks and map how their compositions have changed through time. It turns out sedimentary rocks deposited during Snowball Earth have vastly different carbon isotope signatures than normal sedimentary rocks. This is because algae prefer one form of carbon, the lighter kind, called carbon-12. Sedimentary rocks deposited in water with lots of algae will be enriched in carbon-12. But Snowball Earth rocks have much less carbon-12, suggesting that photosynthetic life was dying out during this time. The Death Valley region also records the global period of thawing that happened after Snowball Earth ended. One of these deposits is called the Noonday Dolomite, and it's what geologists call a carbonate cap rock. The Noonday Dolomite probably formed like this. As Snowball Earth ended, the oceans thawed. CO2 from the atmosphere could dissolve in the oceans again. This formed carbonic acid, which could then fall as acid rain. The acid rain would cause weathering of rocks exposed on the surface, which released calcium. Rivers carried the calcium to oceans and lakes, where it could react with bicarbonate anions to make minerals like calcite and aragonite. Later, these calcite and aragonite deposits were altered to be more magnesium-rich, forming dolomite. In Death Valley, the Noonday Dolomite marks the end of the global glaciation that could have easily wiped out life on Earth. We don't fully understand why Snowball Earth ended, but by 635 million years ago, the global glaciations were over. At some point during this time, Antarctica finally broke off from North America, and Death Valley became the west coast. This was an exciting moment for life on Earth. For millions of years, single-celled life had fought for survival below a global ice sheet. Now the ice was gone. Cyanobacteria from the oceans started pumping oxygen back into Earth's atmosphere, and that extra oxygen would have a major effect on life's evolution. Suddenly there was enough oxygen to support multicellular life. Within just a few million years, strange multicellular organisms evolved. Geologists call them the Ediacaran biota. These soft-bodied animals probably spent millions of years living along the shallow beaches of what is now Death Valley. Today we see only hints of them in remote areas surrounding the park. The Ediacaran biota lived for less than 100 million years, just a moment in geologic time. But they're important to our story because of what they gave rise to. By about 542 million years ago, these once soft-bodied animals had evolved one of life's major breakthroughs: hard parts.
Skeletons and shells were a game changer for life on Earth. If you were a soft-bodied animal and something wanted to eat you, you got eaten. If you had a shell, maybe you survived. For geologists, too, hard parts changed the game. Soft-bodied creatures decay when they die and don't turn into fossils. But bones and shells, these make great fossils. That's why geologists call this time period, which started about 541 million years ago, the Cambrian explosion or the Cambrian radiation. Lots of new animals suddenly appear in the rock record.
We just found these trilobite fossils here on the side of the road here at Emigrants Pass, just south of the park. We think they're probably about 520 million years old. Trilobites were some of the first animals that appeared after the Cambrian radiation, and they tended to live in shallow ocean environments, which is how we know that this area probably used to be marine.
Paleontologists, like Bryn Mawr faculty member Catherine Marenko, map the distribution of fossils to determine what ancient coastal environments must have been like. Years of geologic mapping have shown that during the Cambrian period, most of Death Valley was covered by beaches and shallow water, which left behind sedimentary structures like giant ripple marks.
This whole region was a shallow coastal marine environment for a few 100 million years. It would have been flat for as far as you could see. Rivers would have brought sand and mud down from the mountains and deposited them along the coast. We see a lot of sandstone, mudstone, and limestone during these times, a classic coastal environment sequence.
Over those millions of years, while Death Valley oscillated between beaches and offshore environments, life on Earth changed. Plants and animals crawled out of the oceans and colonized the continents. They did well there, and by 360 million years ago, Earth's continents were covered in swampy forests of house-sized ferns and giant insects. Fish evolved in the oceans, and on land, amphibians, reptiles, and early ancestors of mammals. As the first dinosaurs evolved, something changed for Death Valley. Off the coast, a slab of oceanic lithosphere called the Farallon Plate began sinking beneath the North American continent. This is a process called subduction, and it had serious consequences for the Death Valley region. The subducting Farallon Plate pushed Death Valley up, out of the ocean, and erosion began shaping the stack of sedimentary rock that hundreds of millions of years had laid down. The subducting ocean slab dragged water down below the surface. This influx of water caused mantle rock to melt, and the resulting magma rose up into the North American crust. Where the magma erupted, chains of volcanoes formed, and where it stayed below the surface, it formed vast intrusions of granite. This chain of volcanoes and granite was forming just north of the Death Valley region. These would become the core rocks of the Sierra Nevada mountains. Subduction went on for tens of millions of years, mostly affecting the Sierra Nevadas to the north. But then, about 25 million years ago, something changed. A mid-ocean spreading center collided with the subduction zone. When this happened, the tectonic plates were forced to accommodate a different kind of plate motion. They did this by forming a giant fault, the San Andreas. The San Andreas Fault is a strike-slip fault, or a transform fault. One side moves north, the other south. The San Andreas is actually only one of a whole network of transform faults that formed when the spreading center hit. Another one runs straight through the center of Death Valley. We see evidence of this giant transform fault here, at a hill called Split Cinder Cone. The Cinder Cone is a small volcano, and the Death Valley transform fault cuts it neatly in two. The spreading center subduction event created the San Andreas Fault system, but its effects were far more reaching. The event caused the entire southwest of North America to stretch. Rocks don't want to stretch. If you pull on rocks hard enough, they break. The subducting Farallon Plate pulled on North America from the west, and the plate thinned and then broke in long faults, like this one along the Charlie Brown Highway just east of the national park. Along these faults, giant blocks of crust tilted and slid, forming high mountain ranges and deep valleys. Today, this region is called the Basin and Range, a vast landscape of alternating mountains and valleys. Death Valley is one of those basins, and the mountains on either side are its ranges. You can see this at Badwater Basin. The face of the Black Mountains is the old fault surface. The Black Mountain block tilted and slid up, while Badwater sank down. As the crust thinned, something else happened under Death Valley. Hot material from Earth's mantle rose up toward the surface, causing small pockets of rock to melt. These melted blobs rose through the crust and erupted at the surface as explosive volcanoes. Today, Death Valley is marked by many small volcanoes that formed during this time. The most famous of these sits on the northern edge of the park, Hebe Crater. Hebe formed from an explosive eruption. The magma that was under this volcano probably interacted with groundwater just before it erupted, causing it to explode. The volcano is young. The last eruption might have been between 2,000 and 7,000 years ago, which is nothing in geologic time. The crater itself is a monument to how thin the crust under Death Valley has become. It is some of the thinnest continental crust in the world. As the basin and range topography formed, those basins periodically filled with water, forming giant lakes.
We see evidence of vast lakes filling Death Valley as these basins started to deepen. This is a risky point. These hills are made of sediments that were deposited in Furnace Creek Lake about 5 million years ago. Normally, to form a sedimentary rock, you have to bury sediment under other sediment. The pressure of the overlying layers then compacts the lower ones into a rock. But these hills are barely compacted at all, so there's still more mud than rock. That's why they form these beautiful erosional patterns. The rain easily erodes them into hills and gullies. This is called a Badlands terrain. It's carved heavily by water.
The final lake to fill Death Valley began forming about 185,000 years ago. At its peak, this lake was almost 300 feet deep. Geologists have named it Lake Manly. We can still see the shorelines that Lake Manly carved into the surrounding mountains as horizontal lines that cut across Shoreline Butte in the southern end of the valley. Lake Manly finally disappeared around 10,000 years ago as the regional climate became drier. And as it disappeared, it left behind something strange and ultimately valuable: borax.
Most of the borax in Death Valley was mined several years ago, but the Bryn Mawr mineral collection has some old specimens. This is classic Death Valley borax. It's called cotton ball borax because of its shape. It's rich in the element boron, which is used in detergents. Most of the borax nowadays is produced industrially, but for most of human history, it had to be mined.
The Death Valley Basin used to be covered in globs of borax, called cotton ball borax. And starting in the late 1800s, mining teams would come through to harvest the borax from the desert floor. They processed that borax here at Harmony Borax Works, loaded the material into giant wagons pulled by 20 mules, and carried that across the mountains to the railroad in Mojave.
We also see leftovers of Lake Manly here deposited in Badwater Basin. This is basically just table salt that has evaporated, leaving these evaporites, which is geologically or mineralogically known as halite.
Lake Manly disappeared, the climate dried, and Death Valley became the region we see today. This is the end of Death Valley's geologic past, but not of its geologic story. Geologists today treasure Death Valley, not just as an archive of Earth's past, but as a showcase of modern, active geologic processes. If we're to understand how Earth worked in the billions of years that came before, we must study how Earth works now. This is one of the fundamental tenets of geology. The present is the key to the past. Take these ancient sand dunes in Zion National Park, now compacted into rock. How did they form? What accounts for those cross-cutting lines? To find out, sedimentologists like Bryn Mawr faculty Don Barber examine modern sand dunes, like the Mesquite Flats, just north of Death Valley's Furnace Creek.
So here we are in the Mesquite Flats where there are active sand dunes being formed. The way the sand dunes are formed is that sediments are in the wind coming from this direction. And when they move over the top of the dune and they go to this side, there's a lot more space, so the pressure drops and the sand falls out of the wind and gets deposited on this side of the dune. This creates sort of some layers that we can see that end up getting lithified in the rocks because these sand dunes are really good at preserving material. The sand here is made out of quartz because quartz is a very strong and stable mineral, and the other minerals get destroyed by water or other forms of weathering. So this sand is pretty much all quartz.
Death Valley is a great place to see how wind shapes a landscape. This object here is called a ventifact. It was originally a sort of normal-shaped boulder, but over hundreds of years, the wind has shaped it into this mushroom shape we see now. The bottom of the rock is more eroded than the top because of how wind blows sand. Wind can pick up lighter particles and blow them high, but it can't pick up larger particles. A strong gust of wind might pick up a large grain of sand for a moment, but it'll fall back down. The result is large sand grains appear to hop across the desert floor. These large hopping sand grains have more eroding power than tiny airborne grains, so the bottoms of these ventifacts are often more eroded than the tops.
So Death Valley also shows us a lot about how these halite evaporites are deposited. Some of these salts are left over from Lake Manly, but other ones are more modern. Badwater is the lowest point in a basin that covers 20,000 square kilometers, which is bigger than the state of New Hampshire. That means that all the rain that falls in this basin eventually ends up down here. Along its journey down the mountains, which are on either side of me, the rainwater picks up bits of dissolved minerals, and then when it reaches the basin, the water evaporates, leaving the minerals behind, which forms halite. Each year, only a tiny bit of salt is added to Badwater Basin, but over time this adds up. So below us are more than 1,000 feet of alternating layers of mud and salt. These salts can form really interesting microstructures. So I have an example here of some towers that have formed because when the salt crust, the crust expands, it forms these little teepee shapes. Some other shapes that are found here are hexagonal microstructures. These continuous wet and dry cycles can also force the salt to expand. On a hot day, you can hear the salt crystals expanding and bursting in the heat.
Death Valley's evaporite deposits are exciting for more reasons than just salt processes. Planetary geologists like Bryn Selby Harth think that Death Valley's evaporitic salts are similar to those found on Mars. To compare them, Selby and her students compare satellite imagery of Death Valley to data taken by satellites in orbit around Mars. Mapping these salt deposits on Mars might point to where liquid water once flowed, and where life might once have survived. Death Valley's sand dunes and salt flats are obvious to visitors on the ground. Not so obvious, though, are the sedimentary behemoths forming around the valley's edge, alluvial fans.
An alluvial fan is just a pile of debris. It's sediment that was brought down out of the mountains by streams and deposited in a giant fan on the valley floor. In Death Valley, we see alluvial fans in all stages of their evolution. Here in Golden Canyon, the trail is a narrow chute down which flash floods carry boulders and debris.
The canyon itself cuts down through an older alluvial fan that formed around 5 million years ago. Layers of poorly sorted sediment are still visible in the canyon walls. This cross-section through an ancient alluvial fan shows geologists how alluvial fans operate today, and studying Death Valley's modern alluvial fans shows us how they operated in the past. From the alluvial fans to the salt flats of Badwater and wind-blown sand dunes, Death Valley is a showcase of geology in action. Almost 2 billion years of mountain building, oceans, and stretching have shaped Death Valley into the landscape we see today. But Death Valley's story is still not over. As our climate warms, Death Valley is becoming hotter. In July 2018, it posted its hottest month on record, with average daytime temperatures of 108.1 degrees. On July 24th, the valley set a new daytime high, 127 degrees. Climate scientists predict that warming will continue for the foreseeable future, meaning there may soon come a time when Death Valley's summertime heat makes it uninhabitable for humans, including possibly Death Valley's original people, the Timbisha Shoshone, who fought legal battles for decades for a right to a piece of their homeland. For geologists, Death Valley remains one of the world's best showcases of geologic processes. From the 2-billion-year-old assembly of the Columbia supercontinent, to stromatolites building reefs the size of skyscrapers, to the muds and drop stones of Snowball Earth, the Trilobites, and burrowing animals of the Cambrian explosion. The hundreds of millions of years of the shallow inland sea that covered the West, the crustal stretching and faulting of the basin and range, the explosive volcanoes, and the modern processes of sand dunes, evaporites, alluvial fans, and wind erosion. This one valley is like a geologic textbook that you can visit.